Hello there. Can you people hear me?
Yes, I can hear you.
Okay. Okay, so only few people here. Anyway, in the last lecture, actually, there was one mistake, I think. Yeah, here, uh, in the metastable state, actually. So it was written here the picosecond. So cannot be picosecond. Okay, so probably it can be corrected here. This is a microsecond. Okay, so picosecond even shorter than this one. So it cannot be metastable state. So it was by mistake written here the picosecond. So it's not picosecond, it's microsecond. Okay. So you can correct it in your notes. And other thing, yeah, some of the part of the last lecture was not recorded. And that was from here. So like we have studied the 3 and 4 state laser. And if we compare, then there is a you can see the 3-state laser and the 4-state laser. And as I mentioned in my last lecture, that it's hard to pump 3-state laser as compared to the 4-state laser. The reason, because it has one extra level here and it doesn't have level. So, and the famous actually, the 3-state laser is ruby laser, and 4-state laser, there are so many, but Andy Young and titanium sapphire lasers. Okay, so, and these were the animation, which I explained actually in the last lecture. And what it shows that the levels and metastable state and then photons. So this is for the 3-level system here. This is for the 4-level system here. And the level 1, which is a ground level, and the excited level is this one, which we call the pump level as well. And this is a metastable state, and this is a photon. So when the metastable state actually is filled up, so you can see the lasing in the form of photons are coming out. And similarly here we have a ground, the lowest one, and the lower energy level. Then we have metastable excited state. And what happened when in the ground, actually, when the ground is populated, there is no laser action. And other levels are empty somehow. But as soon as the ground is become less populated, then you can see the lower level. And the excited level first is populated, which is also called the pump. And from there, after that, you get that metastable level to fill it up or to have more population. And from here, when metastable level is populated enough, then you can have a photon emission when it decay from the metastable to the lower energy level. Okay, so these were the animation which I explained actually in the last lecture, but it was not recorded in the last few slides, so I thought to add it. And after that, this is also I showed that how the levels are. This is a 3-level system here, and this is a 4-level system here, and how it behaves. You can see that this is the ground, metastable, excited state. Here is the ground, low state, metastable, and excited state. Same thing which I have shown in the last slide. Okay, so ground is populated. Then after that, it goes to the higher state, and then from high to the metastable state. And when you pump it, then from metastable state to the ground state, and laser action is happened. Okay, so, and this was the principal component of laser. So principal component of laser that you can see here, it should have a cavity mirrors, okay, and it should have a pump, which you can see here, green one, and it should have a gain medium. Okay, so what exactly happened? We know somehow already that the photons are generated in the gain medium, and then these photons are amplified by using the cavity mirrors. They are moving to and fro here and here and here and here. And when it's amplified, one of the mirror is partially polished, and one of the mirror is fully polished. Okay, and this thing only happened if we supply or apply external energy sources like a pumping. Okay, and this is whatever laser you have. These are three components, principal component of all kind of lasers. Okay, so it should have a gain medium, should have pump, and it should have a cavity mirrors. Okay, so, and after that, this was the case, like the conventional, say like this one side of the cavity, the mirror on the one side of the cavity should be partially polished so that the laser action, so laser can be emitted from this cavity. So it has to be, reflectivity has to be less than 100, and other side reflectivity has to be 100%. And this is the pump which is necessary. Okay, and you know already these things, the cavity to mirrors, and the pump source is energy, and the gain medium is also called the laser medium. And this is the uh, action, uh, what happens in the cavity, inside the cavity, atomic level. Somehow you can say that this is green, the blue one is ground state, green one is excited state, and the red one is excited state, and the green one is the first excited state. Okay, so you can see when the ground is more populated, and after that, what happened? The second excited state, and then the first excited state. Okay, the green one. So when the green one are in a majority, you can see the photons are generated and they start moving to and fro. And then it's again de-excited. Okay, so ground is populated again, and the same process is repeated. And this yellow one you see is a pumping. Okay, so this was the few slides which was not recorded in the last. Okay, so now I will move to the next one, which is the actual one. Okay, so I hope you people can see, and let me see how many people are there actually. Okay. Zanfar, are you there? Arusa Hadi.
Yes, sir. Assalamu alaikum.
One Islam. Salman, by the way.
Ji?
Where is Salman?
Sir, he is on the way to home.
Okay. Okay, thank you. So, okay, let's start now. Lecture number 5. Okay. And what we study in this lecture, you will see. We'll move to the first slide, actually. The second, you can say. So, in the last lecture, what we studied at the end. First, we studied the energy levels, 3 and 4 state lasers. And at the end, we just touched actually the concept, the principal component of the laser. And the principal component of the laser, you know that the resonator, cavity resonator, and then you have a laser medium, and then you have a pump source. Okay. And the first thing which is important at the moment, not at the moment, is always. All three, I mean, the components of a laser are important. Resonator is somehow is more important in the sense because it's used to amplify the photons. Okay. So what exactly optical resonator? Two mirrors face to face each other, like you can see here. It can be a concave mirrors, it can be a convex mirrors, and it can be plane mirrors. I hope you know that what are these convex and concave mirrors. Okay, so it what it does actually, optical resonator or cavity, when the photons are generated in the laser medium, it amplifies it. How? When it moves to and fro like this. Okay, and it depends that as I mentioned, one of the cavity mirror, this one, let's suppose we call it output coupler. Okay, so output coupler means that the output to take the output from this side. And usually this one is partially polished. What is partially polished? Partially polished means that when a laser, the photon actually inside the cavity, is built up, increased to certain limit, then this mirror let it to pass through, let these photons to pass through. But below that limit, no, until it built to a certain level, then it passed through. Okay, that is why it's called partially polished. One side is fully polished because on that side, it's always confined. The photons are confined, will never go out of the cavity. Okay. And in this case, many times not many times, infinite time maybe, the photons are generated and then amplify, population inversion happens. And from metastable level to the lower level, the photons transferred and the laser is, atom is transferred and laser emission is happened. Okay. And this resonator has to be straight, okay, parallel to each other, very much parallel actually. You'll see later on detail, I mean, there's some alignment or something like this. And if you see in the yellow portion of the slide, so what is written there? That substantial amplification occurs if the light beam is reflected several times. Okay, several times, I mean, uncountable, you can say. Okay, and it should pass through the active medium each and every time when it bounces from one side and it moves to the other side, it should pass through the active medium. Okay, so that all the photons move in one line, added with one photon, 2, 3, 4, 5, 6, 7, 8, 9, 10, and etc. etc. Okay. Now, it's also called cavity, it's also called resonator. I mean, it depends, but both are okay to say. Now you can see here on this slide that on the left side, this is a simple figure that it shows that M1, M2, mirror 1, mirror 2, and this one is a mirror where the output, we check the output, and it's called OC, output coupler. This one is 100%, almost 100%. This side has almost 100% reflectivity, and this output coupler, it may have like from 95 to 98, 98 to 95%. Okay, and the gain medium is here. Okay, so this is, if you see like this is the animation actually. Let me go back, and then here you can see how it acts. I mean, this is just animation. I mean, the move to and fro, and then emit at the other end. Okay. So what is written here, as I explained, 99.5%, and here is 98 to 95%. Okay, so our output coupler. And as I mentioned that M1 and M2, they are supposed to be very much parallel to each other. Okay, for a proper cavity, for a proper laser action, both these mirrors are supposed to be like 100% parallel to each other, whether it's convex, whether it's concave, or whether it's plane mirrors. Okay. And these M1 and M2, they are supposed to be coated. Now, this is another topic actually, if you go in detail, that I don't know how many people know about, how many people have seen the mirrors, the mirrors we use in the lasers or something like this. But you people know the mirror which we use at home. Okay. And this mirror actually, it's a coated. Okay. It has a coating that it reflects, I think, all the portion of the light. Okay, like white light or whatever it is. So that is why we see that everything is reflected from the mirror. But some of the mirrors is also possible that they only emit certain wavelengths. It's not emit. Emit, I'm saying, I mean, it's not a correct word. Reflect. Okay. So some of the mirrors are there. In normal case, all the light is reflected. Okay. So this is a white light. If we have some mirrors which only can reflect that red or green maybe, or any other color. Have you seen such kind of mirrors that reflect only a certain wavelength? Have you seen any of you? David, have you seen this kind of mirror? Reflect only one wavelength?
Yes, usually they have like a filter, and also if going to be the reflected light red is like a red color, the mirror.
Mhm. Okay. Okay. Ihtisham, have you seen?
No, sir. Actually, I didn't have seen any mirror with uh, the specific wavelength reflection.
But have you seen the laser?
Yes, sir. I have seen the laser.
So what kind of laser have you seen?
Sir, it was TI sapphire laser, and I haven't given a chance to see it closely. I have seen it from a distance, so I didn't recognize little details from the system.
But you did experiment with that laser?
No, I don't have any experience with this experiment.
Then why are you saying you have seen? Where did you see?
Sir, actually, in Nilo, laser,
Oh,
uh,
okay.
there is an institute, National Institute of Laser and Electronics.
Mhm.
Oh, once I have visited there, and I saw their
Oh,
setup.
okay.
They were using it. They were using laser for generating ions,
Yes,
I
yes.
think.
Okay, okay, okay.
So
So, I mean,
I did that.
okay, you just visited there, but you haven't worked with any kind of laser.
No, sir, I don't have.
Okay, okay. Okay, Mauricio, have you seen the mirrors which only reflect the certain lights?
Um, well, I um, in the lab of the university, I worked with a helium neon laser,
Okay.
and I saw the mirrors, but well, I didn't have the opportunity to prove it with green light, so only with red light.
Okay, okay, okay. And now you are also working with some lasers or not?
No, well, it was for me. For me, sorry.
Yes, yes, for you, for you.
Um, well, it was part of the course of an advanced physics laboratory, but it was just take data and do some fits on the data.
Okay, okay.
Curve fitting.
Okay, okay, okay. Good, good. Okay, Arusa Hadi, have you seen this kind of mirror that only reflect a certain wavelengths?
No, sir, I didn't see.
Have you seen any laser?
Yes, sir, I see dye laser and Nilo.
Okay. I mean,
Yes,
just did you touch it?
yes, sir, but I didn't work on it. I
Uh,
just see it.
okay, okay, okay. So dye laser, it was dye laser, are you sure?
Yes.
And what kind of dye they were using?
There were different dye they are using, but I didn't focus on it at that time.
Mhm. Okay, 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 okay. It's very interesting to see the lasers, but unfortunately in Pakistan you don't find many places. Yeah,
Yes.
yeah, okay, okay. So, Amna says, have you seen something like this? The mirror which can reflect only any one wavelength?
Sir, I don't know if it was the same thing or not, but in our BS, we performed an experiment to find the speed of light. So we used laser actually to find the speed of light, and we used mirrors that reflect only red laser light.
Yeah, but I think that was not they were the general purpose mirrors. And
Yes, sir.
yeah, that was not that kind of mirror which I'm asking. So Tahura Hadi,
I didn't see.
have you seen the laser by the way? Great. Salman, you are there now?
Yes, sir. No, sir, I didn't see.
Okay, okay, it's okay, no problem. Salman, are you there? Salman. Okay, anyway. Okay, so there are some kind of mirrors that, and it's very expensive mirrors. We call it, it's a dielectric mirrors, okay? And it has a certain coating that it reflects only that certain wavelength of the light, and rest of the light passes through. And like, it depends. I mean, like in advanced lasers, we use this kind of mirrors, and these are very expensive. That it only stops the IR, infrared region, and let the other wavelength to pass through. Okay, and this is called the last, actually here, the last line. It's dielectric mirrors or dielectric coated mirrors, something like this. And these are very important in the cavity. And in this way, we can have more efficient cavity, in the sense there are some other wavelengths are also generated, because you cannot make a perfect light, laser light. So to block the other wavelengths, you need to suppress them, actually. You can use a certain kind of mirrors which are only coated for a certain wavelength. So in this way, you can get.
Yes, sir. Hello, sir.
Yes, yes.
Sir, I'm on my way to home while driving.
Okay.
So I connect, but it's very difficult to continue because constantly the signal is dropping.
Yeah. It's okay. It's okay. You can listen to the recording.
I will watch the recording, inshallah,
Yeah.
sir.
Yeah. Okay. Okay.
Okay, sir.
Okay. See you in the next
Please.
lecture.
Thank you, sir.
Okay. So let's move to the next slide here. We have simple animation. I mean, what it shows that the photons are there in the cavity, and from one side they are coming out, and it's like not exactly showing the laser action, but it shows that the light as a particle coming out from one side of the mirror. Okay, so now it's very important thing, because there are a couple of I think candidate here who studied or who were good in electronics or something like this. If you remember, in the first lecture, I said that the laser is offspring. Okay, optics and electronics. So optical resonator, or the optical cavity used for the laser, or resonator can be for other purpose. We can use this word for the other purposes as well. This optical resonator is very much similar to the electronic oscillator. Okay. What is electronic oscillator? You can see here. Amplifier, okay. And then you have output, and output is fed back to the amplifier, and this process is repeated. Okay. And it's amplifying, and something like this. And sustained. The oscillation is sustained. It's maintained. And what exactly happened in the optical resonator? Oscillator, what actually oscillation means? The oscillator is generated and then sustained. You have an amplifier here, and amplifier, what is that? Amplifier is a laser gain medium. Okay. And these mirrors are as a feedback loop is used here. Okay. So the photons are generated, they move like this, to and fro. So it's a kind of feedback system. Okay. And at a certain level, we get the output. And the same thing here in case of electronic oscillator. Okay. So the process is very much similar, maybe not 100% similar, but very much similar to the electronic oscillator. So in electronic oscillator, what we do actually, an amplifier actually tuned to a specific frequency, 10 hertz, 20 hertz, whatever it is. And then this oscillation fed back to the input of the amplifier. So that same tuned frequency, a same frequency is maintained, okay, and continue oscillations are generated. Okay, so if it is like this, then it's like continue. It will never stop, okay, until you turn off the feedback system. Okay, and like here you can see what is written here. When you turn on the oscillator, the signal that appearing at the input of the amplifier, okay, and amplified output and amplify again. So if we start, when you turn on this kind of system, in the beginning it's a bit of unstable, but with the passage of time it becomes stable. And the same thing happened with the optical isolators, not isolators, sorry, oscillators. Okay, so when you turn on, in the beginning you see light which is not coherent. That could be a spontaneous emission or something like this. Okay, and this light slowly with the passage of time, it's not like minutes, it's a fraction of minutes or seconds, you get stable output laser. Same thing happened with the electronic oscillator, sorry, not isolator, oscillator. Okay, sorry. What you see here in this animation, that is you can see on this one, that is electronic oscillator signal. Okay, signal is maintained and amplified continuously. And the red one, it shows the optical signal, and there is a dotted line. This dotted line, actually what it shows, this is the dotted line which passed through the optical coupler, output coupler, from which side we take the laser out. Okay, probably it may not understand. I mean, for you it's difficult to understand at the moment, but maybe later on. It's just to show that how these waveforms are formed. And if you see in the form of like a photon, here you can see it's moving to and fro. And in case of electronic, it's like a wave. Okay, and it's continuously building up. And at certain point, it comes when you get the output from the electronic oscillator and from the optical oscillator or resonator. Okay, it's very similar to this resonator is very similar, or in some sense you can say it's a Fabry-Perot resonator. Fabry-Perot resonator, actually two mirrors side by side, parallel to each other, very close to each other usually. If we arrange in this way, we form it. It's called Fabry-Perot resonator. Okay, and because in case of a cavity or the laser resonator, two mirrors are supposed to be parallel to each other. So this kind of cavity we may also call the Fabry-Perot resonator. Okay, and a pair of mirrors, okay, that in case of optical resonator, it can be a Fabry-Perot resonator, we can call it as well. And now these mirrors, as I mentioned, these mirrors can be plane mirror or can be curved. Curved mirror means it can be like this or can be like this, convex and concave. Okay, the light coming from here and the light here. I know that you have studied, I assume You people have studied this from the high school, this kind of convex and concave mirrors. Okay, so why it's supposed to be parallel to each other, that it should utilize all the light which is produced in between these two mirrors. Okay, if these are not parallel to each other, the light will not be trapped and it may go out. Okay, so if it is like this, obviously light will go out. Okay, so it will not be trapped. So as I mentioned, the one side is partially polished, partially reflecting, and it means that the light can be transmitted from that side. Okay, so this is the same thing which we went through in the few last slides. Just the name is Fabry-Perot, because Fabry-Perot resonator are also having the straight two plane mirrors or any other kind of mirrors. Action and working. Okay, so what exactly happening here? That you know that we cannot have 100% efficient laser medium. Okay, and there is always losses in the medium, and we have to overcome the losses to have a, efficient laser light. Okay, so the loss and gain has to be balanced. Okay, these losses are because of gain medium, because of the mirrors, and because of the surrounding areas or the container or whatever it is. It's a tube or it's a kind of cylinder or whatever it is. So we have to overcome these losses, and so that we can have efficient laser action. Okay. If we cannot overcome the losses, we may not have a continuous laser. Continuous means we may not have a sustained laser action. Okay, it may stop after a while. We know that the end mirrors, they reflect strongly back to the medium. Okay, and stimulated emission is sustained because of the pump action continuously. Okay, and we need one of the condition, the property of the laser, that it should emit one single wavelength, ideally. Okay, that is called line width, but it's not 100% possible that we have such a perfect laser. So there are always some other frequencies in a small fraction, but it's there. So laser is supposed to has one wavelength, so it means that it should oscillate at one frequency. This is your cavity. Okay, the laser, if you consider the waveform, okay, so the wave is supposed to be oscillate at one frequency, single wavelength. Okay, I cannot draw here properly. So light has to be monochromatic. So other light, other wavelengths, if there are any, it has to be suppressed. And how it is done, as I mentioned, by coating the mirrors with a suitable material, that is dielectric coating, which I mentioned. Okay. So effective optical resonator, you should have mirrors with certain coating so that only the desired wavelength can pass through and we get output. Rest of the wavelength to suppress, because there will be definitely. Okay. And in the gain medium is useless if you don't have a cavity. Okay. So cavity is essential. You can have a very, very, very long gain medium, which is practically impossible. But without cavity, actually you cannot sustain the laser action. Maybe you can have one blink or one shot or two shot, maybe. It depends what kind of laser, but it's not possible to sustain the laser action without cavity. If you see here, this is a helium neon laser. Okay. And if you open, it's a black jacket around it. If you open it, it's like this, the tube. Okay. And the gas is filled inside helium and neon with a certain percentage. You may not see, or maybe, someday, if you can open any broken helium neon laser. This is small, very small cavity mirror on this side and very small cavity mirror on this side. Okay. And these are very small size, like very, very small. Okay. We don't need so big because the laser, it has to be fine-tuned. Okay, so these are the mirrors. One side is partially polished, other fully polished. Okay, and when the light is laser light is generated here, then it moves to and fro, and one of the side it comes from one of the side it comes out. Okay, so in actual, why I'm showing this thing, that how actually, it looks like. Okay, so the cavity is like this. Not necessary the mirrors to cover the whole cavity. Okay, and here on this portion, small portion, the cavity mirrors are there. And it's not necessary, as I mentioned, that to have a plane mirrors. Okay, it can be curved mirrors, like convex mirrors, concave mirrors, one plane mirror, other convex mirror, other concave mirror. That all the possibilities are there, which we study later. This is overall laser action. You can see it started from here. Okay, A few photons are generated, and then B is multiplying, C is more multiplying, and now it's excited, more excited, here more, and finally, when this stage is reached, we call it equilibrium state. So the laser action is sustained. Now laser will work until the pump is there actually. So sometime, you need a certain pump energy to maintain and to start. So once you achieve it, then you can have an equilibrium state, like continuous operation of the laser. So when it starts in the beginning, you don't have a laser actually, in a fraction of seconds. And usually you don't have a laser, but you have a light. If it is like a red wavelength, red light, maybe green wavelength, green. So that is not coherent actually, that is spontaneous emission, which is naturally occurring. And this spontaneous emission actually build up, stimulated, and then we get the laser action. Okay. Okay, so what do you see here? It may confuse you, or it may not confuse you, or it may help you to understand. In any case, the animation is not real. You may understand more maybe. So what is on the left what you see on the left here, this one, I use a single wave building up. Single wave, it means single wavelength. Okay, it can be 800 nanometer, 500, whatever it is. So what is happening here? It's building up. You see the amplitude is increasing, and at certain level, you can see it start emitting. Okay, so this is what it shows. This is the laser action, and it's a cavity here. In the beginning, the photons are multiplying slowly, not very slowly actually. But it comes out at a certain time, okay, when this wave is built up enough. Then this output coupler mirror allow this wave to pass through, and we have output laser. Below certain level of this wave, like here, it's oscillating, but it's not coming out. Okay, so it's oscillating, but it's not coming out. So this oscillation here is not shown like to and fro, but I just show in the form of one wave. And so this is the laser action. Now come on the right side. Here, upper one, what I showed here multiple waves. Okay, there are like 5 waves somehow, and they are coherent to each other. Okay, so it means it's a so it means it has one wavelength. Okay, just to demonstrate, I added number of waves here, and in the beginning the amplitude was small, but with the passage of time the amplitude increased, and when the amplitude at a certain level is reached, we see the output here. Okay, down here on the right side there's a similar kind of thing, but here the amplitude is not increasing. Okay, just showed that the more waves are added and we get at the output. So this is not a very correct demonstration. Here, this one and this one is close to reality. I'm not saying 100%, but maybe you can grasp some idea how the resonator cavity it works. Okay, single wavelength and multiple wavelength waves are building, and at certain stage or certain time, when the amplitude reaches to a certain value, we see the laser output. Okay, and at certain level, the partially polished side of the cavity let the light to emit something. Okay, okay, let's move to the next slide. What you see here now, it's a gain medium. First thing was what? The resonator, essential part. Now we have gain medium. Okay, what is gain medium? Gain medium is a laser medium. What kind of medium it can be? It can be gas, it can be solid, it can be liquid, it can be chemical. Okay, it can also be air as well. So what you have here, that is simply it shows that the photons are multiplying and we get the laser output. Okay, one is output coupler. Other one is fully polished. Okay, and this animation also you can see how the photons are multiplied. Okay. Okay, so what is written here? The number of photon increases in time. Okay. With the passage of time, when it is pumped, then these photons are increasing. But why it's increasing? Because of the cavity. To and fro, passing through gain medium again and again. Okay. And increase in time. But the condition, you should keep in mind that we already know that it has to be population inversion, metastable, highly populated, and one side has to be partially polished. Okay. So gain medium is ineffective if you don't have this kind of things. So population inversion is happen in gain medium, but output coupler stuff is in the cavity. Okay. So several round trips. So obvious, this process results in a lot of photons, generates a lot of photons. Okay. But as I mentioned before, the stimulated emission will be lost through the walls of the cavity. This is the question. Stimulated emission will be lost through the walls of the cavity. How? Number of reasons. If the cavity is not aligned properly, okay, and some other technical is a pump is not enough. Okay, so number of reasons, but stimulated emission, it happens in the gain medium where the population inversion happens. Okay, and then the action of the cavity is started. So there are a number of gain mediums. Okay, so you know already that it's solids. We have anti-Yag, neodymium, and yttrium aluminum garnet. Ruby is also gain medium. Titanium sapphire is also gain medium. Anti-glass is also gain medium. Okay, in the solids. And in the liquids, we have a dirhodamine 6G. And in the gas, we have a krypton, nitrogen, helium, neon, laser, carbon dioxide, etc. There are so many. Semiconductors, the aluminum, gallium arsenide, and some other materials. All these are gain mediums. Okay, just for just to you people to know that these are the gain mediums. Okay, and this is anti-Yag. This medium, it looks like in the form of a rod. Okay, and this thing I mentioned already, that in the last lecture, dopant and the host. Okay, so the dopants are important. Without dopant, we cannot have a laser action. Okay, this is the anti-glass, and here if you see, this is a nitrogen laser, dye laser. Okay, and these are the crystals. Titanium sapphire is a gain medium. Okay, and in case of a diode or semiconductor, this is how does it look like. Okay, so these are the kind of gain mediums, and these are, I mean, it has to be used within the cavity for the laser action. Now pumping. Pumping is source of energy, okay, to create a population inversion. Okay, there are different kind of pumping methods are used. Light pumping can be used, electrical pumping use chemical reaction pumping, and so many kinds of pumping methods. So population inversion, and to maintain the population inversion, pumping has to be continuous. Okay, so that atom have to be raised continuously to the excited state, goes to the ground and then excited again, goes to the ground and then excited again. Okay, so this is the function of pumping process, okay, to maintain the population inversion. And in the pumping process, you already know there are a number of energy levels are involved, like the highest one is a pump level. Then you have the metastable, then low level, then ground level, or something like this. So without level, pumping is useless. The laser, the medium should have some certain levels. Okay. And important thing is metastable level. And metastable level is linked with the dopant. Okay. So if I tabulated the type of lasers and the pumping mechanism or pumping schemes, you can see here the gas laser, and major gas laser is helium neon, argon ion, nitrogen, carbon dioxide, or etc. etc. The pumping method or mechanism for this kind of the gas lasers, it can be AC or DC electric discharge through the gas medium. Gas medium is the laser medium. Very high voltage. Okay, you have two electrode and the filled with the gas. This is positive, this is negative, and you have like 10 kV or something like this. And discharge happen here. It excites the atoms, okay, and then regular process of lasing energy levels and etc. So gas lasers are necessary to be pumped with the AC and the DC. It depends what kind of gas medium is used. Okay. In case of solid state laser, you have a ruby laser, you have ND-YAG laser, you have fiber laser, also categorized, titanium sapphire also in the same category, and ND glass and more as well. And this kind of gain medium or the laser medium are pumped. It's called optical pumping. They are pumped by optical pumping source. And optical pumping source, it can be like flash lamp, or it can be like another laser, another semiconductor laser maybe, or any other kind of laser. So this is basically essential. You cannot pump the solid state laser with the electric or AC or DC electrical charge. And similarly, gas laser cannot be pumped with the optical pumping source. Okay. So the third one is semiconductor laser. Semiconductor laser, it's like all the normal the semiconductor devices. You always need a DC current source. Okay, DC source. And Mostly it's like this, but some of the modern kind of, which I don't know exactly the main theory, some kind of semiconductor laser can also be pumped with a electron beam pumping. Okay, so if I get knowledge about it, I will show you or explain you this one a bit. But at the moment, you have to keep it in mind that a DC current source is used to pump the semiconductor lasers. Okay, aluminum, gallium arsenide, or something like this, whatever it is. So the last one is in the table, the liquid dye laser. Dye laser usually it's optically pumped. Because it's a liquid, and from the liquid the light can pass through as well, and you cannot use like AC or DC electric discharge. We just use the optical pumping, another laser actually, basically another laser to supply the energy, to apply the energy, and to start the laser action, population inversion, and etc. etc. So gas laser, they have a DC, AC, electrical discharge as a pumping source, solid state laser with an optical pumping source, and semiconductor lasers are also DC current source is needed as a pump. And liquid or dye lasers is optical pumping. Okay, and the chemical laser, actually that is a different story. In case of chemical lasers, two chemical they react to each other, and that is the population inversion is started. Some reactive agents are added in that chemical lasers, but it's a complex theory. It's not a scope of this course, so that is why I'm just giving you a little link about it. Pumping sources, if you see here, just to show you the what kind of pumping sources are used, and these are flash lamps, different kind of flash lamps. Simple flash lamp like xenon type, argon type, something like this. Here, the real picture of these the flash lamps, and here, this is a fiber optics pumping setup. It's not simple to understand the fiber optics, because for the pumping of the fiber optic we use diode lasers. Okay, diode lasers. So one thing we know that the pumping source provide energy to initiate the stimulated emission and population inversion. Okay, and laser diodes are used for pumping the fiber lasers. Okay, fiber lasers we use for the fiber laser, we use the diode pumping. Diode pumping means another laser, but miniature, very small, like it can be a diode or semiconductor laser. Okay, and optical pumping, as I mentioned, optical pumping means use a flash lamp or any other laser. Okay, like in case of a titanium sapphire, we use another laser to pump the titanium sapphire, that is green color. Okay, and for the gases we have electrical discharge, and for the chemical lasers, as I told you, that the arrangement they make to when the chemical reaction started. So then this is the pump action actually in the chemical laser. And electrical pumping in the PN junction, as I mentioned. So this is here, this is the arrangement which may not be clear to you, or maybe it's confusing. In the later stage, maybe I will show in detail. Maybe. So this is the diode pumping in case of fiber laser, and this one is flash lamp. Flash lamps, this kind of flash lamp is used for the ruby laser. Okay, same. This kind of flash lamp is used for the ND YAG trade. This one also. Okay. Here, you can see a nice colors here. So pumping source, the continuation of the pumping source. Here you can see different pumping flash lamps. So it can be a helium, neon, argon, krypton, xenon. Okay. So it depends what kind of laser is used, what kind of gain medium is. So according to that, the flash lamp is chosen. So it depends. I mean, we'll see in next slides that because the light is supposed to be absorbed in the highest level, which is called the pump level, excited level. So if the light is not absorbed in that one, then your pumping is useless. Okay, it will not produce a population inversion as well. On the right side, what you see here, this is a pumping for the fiber optics. Okay, so this is like, it's a diode. Inside of it, there are a matrix of diode, number of diodes. Okay, the laser diodes. So these laser diodes are guided through this fiber optics to the fiber laser. Okay, so this is a pump source for the fiber laser. Okay, and fiber lasers is the most popular in these days because of many reasons. It can generate high powers and etc. etc. And here you can see the flash lamp and their size. Some are very small, some are big, and it depends the what dimension the laser medium is used. Optical pumping actually is more common, you can say, in most of the laser. Whenever we use a solid state laser, we need a optical pumping source. And how it does actually, it illuminates intense illumination to the gain medium. The light comes out from the flash lamp, very intense light, and it's illuminate the gain medium. Okay, in a tight arrangement, so that the light should not escape. Okay. Usually, the optical pumping is used for the laser medium who are transparent. If the laser mediums are transparent, then we use mostly the flash lamp pumping source. Okay. And the last point here, if you see, very important. If the pumping level of the atom is narrow, pumping level, the highest level, we must use a pump photon of only specific frequency. Okay. So if the absorption band or the pump level of the atom is broad, that broad means if it can absorb many light wavelengths, then it's okay to use a white light, any flash lamp. But if it is narrow, then you must use the pumping source with a specific frequency, like in case of a titanium sapphire or something like this. Okay. Here, what do you see here? These are configurations and assembly of the ND-YAG lasers, specifically ND-YAG laser. Okay. And this arrangement is necessary to have a laser action. Okay. Here, if you see, this is a closed elliptical arrangement. And here you have a laser medium, that is rod and YAG. And here you have flash lamp. Okay. And similarly here, this is circular arrangement Okay, this is line arrangement kind of, and this is multiple ellipse here, and this one is double ellipse, and this one is axial type. So what exactly happening here? This is a flash lamp and this is a laser. When flash lamp, it shines, it's turned on, the light is reflected from all the sides and it goes here. Okay, its focal point is here. So light concentrate here, reflecting from all the sides and concentrate here. Same thing here. Here we are using two flash lamps. It's more diffused, condensed kind of arrangement. Okay, the light from both the sides concentrate on the center, which is the laser medium. And here the light is reflected from both the sides because it's a ellipse, and it's concentrate here. And similarly, there are multiple flash lamps. So all the light is concentrated here. Very strong pumping. And axial means that there is certain kind of flash lamps like this kind of arrangement, and the rod is inside. Okay, so the light is flash lamp pump source is outside and the rod is inside. So this is called axial arrangement, like this one, this kind of arrangement. The rod is inside. Okay, so this is actual pictures. You have this arrangement like this. This is your rod, this is your flash lamps. Okay, and this is sealed. Everything is sealed, and the water is flowing through because to avoid the damage, because heat up too much. And this thing is inserted here. Now, similar kind of arrangement here, two flash lamps here. This is a rod. Okay, and here also this is a single flash lamp here and the rod. Here also the rod and flash lamp, single, one side like this. Okay, so in the next animation, maybe you can understand somehow more. What is happening here? This is your rod, and these are all flash lamps, and it's shining on it's focused on the this laser medium, which is rod. Okay, can be crystal or something like this, but in case of anti-Yag, usually it's rod. So it's concentrate here, very strong pumping, and then definitely, I mean, it emits the laser, and it's high power kind of laser. They have this kind of arrangement. Okay, and this is for to generate the laser. Okay, and after the generation, you use the cavity mirrors, both the sides to amplify. Okay, so these were the kind of optical pumping setups. Now, for the optical pumping, to understand a bit, as I mentioned that each and every material, laser medium, it has an absorption spectrum. Okay, this absorption spectrum, to measure this absorption spectrum is very important so that we can know what wavelength pump we can use. Okay, this is the absorption spectrum of the Yag. So selective pumping. If you see the absorption spectrum, whenever the scientists, they work on to make a laser medium, even the material scientists or something, one thing they do to have absorption spectrum. So with the absorption spectrum, they understand in which region this medium or this material can absorb the light, which is necessary for the pump action. Okay, so this is the absorption spectrum of the Yag. And if you see this portion is very important here. Okay, So between this portion from 700 to 800 nanometer, we can see that this is the absorption band range. So absorption band range is this one, from 750 to 800 nanometer is absorption band. Okay. So 50 nanometer is absorption band. Okay. And keeping this in the mind, we have to use the pump source which cover this region. Okay. Which can cover this region. Similarly, ruby may has a different, and some other material may have a different absorption band. Okay, so accordingly, we have to choose the different kind of different wavelength pump sources. Okay, here this is absorption band, and we can also use a white light if white light is coming. Also include this wavelength range, which is which can be seen in the laser medium, the absorption spectrum of the laser medium. Okay. Here, what you see here, example. Okay. We have a xenon lamp as a pumping source. And this one is rich in blue and green color. Okay. So around 400 and 500 or something like this nanometers. Okay. So YAG actually does not absorb the light, particularly in this region. Why? Here, you can see clearly. This region is very weak region. So YAG cannot absorb the blue and green light. So the YAG should not have a pump source whose wavelength is in this range. Okay. And so if we use the xenon lamp pump source for YAG laser, then it's useless. Useless in the sense that you will not achieve what you want to achieve. Okay. So on the other hand, the krypton in another flash lamp, okay, and it absorbs the light. Sorry, it emits the light. Output of the krypton lamp is around 750 to 850 nanometer. Okay, krypton lamp, it emits light in the blue and green region, something like 400 to 550 or something like this. And krypton lamp emitting around this region, which is suitable for the YAG laser and the YAG laser. Okay. So in this case, we have to use a pump source which cover this portion. Okay. Now, ruby laser, the ruby laser. Ruby laser's absorption band here the ruby laser, if you see the band here, these are the band for the krypton and xenon. Okay, so krypton is very much suitable for the YAG, and this one xenon is very much suitable for the ruby. Why? Ruby laser is absorption band is in the region of yellow and green. Yellow and green. It means from 500 to 600, something like this. Okay, so xenon lamp have much higher output in the yellow and green portion. Blue, green, yellow, they are not very far from each other. Orange also comes in it. Okay. So xenon lamp rich region, xenon lamp can be used to pump the ruby laser, and this one to use for the YAG laser. Okay, and this is one of the examples that the absorption band is very important to know that in this way you can know that what light pump source is needed for a certain kind of laser medium. Okay, and the absorption band, if you see the absorption band for the YAG, for the ruby, for other, so it will show you that this portion it can absorb the light, and this portion it can absorb the light, and you use that kind of pumping source to have effective pumping. Otherwise, useless pumping. Electric pumping. Electric pumping, simply electric discharge is happened between the two electrodes inside the tube, and the tube having a gas enclosed, which is as a laser medium. Okay, so here you can see this is one of the example. These are just discharge tube, and you have electrode and high voltage. Usually very high voltage is the kilovolt, 30, 40, 50 kilovolt range. And this tube, like you have seen in the case of helium neon laser, that the cavity mirrors are is attached to the tube. It's similar here. Okay. Electrons create a population. Okay, what happens actually? What happened in electron discharge actually? There are so many electrons. Okay, high voltage discharge happen, and these electrons are knocking out the atoms. Okay, and in this case the atom may collide with each other. Okay, and so it's a random you can get some kind of population inversion. Usually in the case of gas laser, they have very broad kind of pump band. Okay, so electric discharge can be used. But the detailed theory of electric pumping, that is not a scope for this course. It involves certain processes, but I'm not going to mention here. So different kind of gases are there, nitrogen, carbon dioxide, laser, but arrangement is like this. And this is electric pumping way. And for the diode or the semiconductor, it's very similar to the electronic semiconductor devices. You connect positive and negative terminals to the power source, usually current source in case of lasers. Okay, and then N-type, P-type materials, hole, and the electrons are generated, and the junction, forbidden region, all these things which we study in the electronics is the same processes. In case of only the difference is that the material is not silicon or germanium. You have a different materials, aluminium, gallium arsenide, or something like that. Okay, and this one, electric pumping and the semiconductor, it is definitely, it helps to have here to combine the holes and electrons, and holes and electron when they it's a forbidden region and they combine with each other, you may have some laser action. In simple words I'm telling you, otherwise theory can be complex. Okay, so like here the current passes through the interface between the two sides of the material, p-type, n-type. Okay, and it creates one side can be hole, can be electron, okay, another side similarly can be non, it depends p-type or n-type, okay, and then the population inversion is created at all these things are happening in the center, a junction point, which is called the forbidden region as well. And the laser action happen from the junction of two type, n-type and p-type materials, okay. If you open it, it looks like this, and it's very cheap. This is especially this one is very, I mean, it's maybe 100, 200, 300 rupees, or maybe it's $1, $2 or $3, easily available. Chemical pumping. Chemical pumping actually is, as I mentioned, the chemical reaction to happen. What do they do actually? They use two chemicals and separate them in the cavity kind of arrangement, a vessel or something like this. And with a certain electronic arrangement, they use kind of shutter when both the materials, they match or react each other, and then the pumping is started and the laser action happens, okay. Like here, when the hydrogen combined with the fluorine to form the HF, hydrogen fluoride, and heat is generated, that heat causes the definitely it's a chemical reaction. And in case of HCl and HF and coil, chemical oxygen, iodine, they keep separate all the chemicals and then they combine, the reaction happen, and then you can have a laser action. Usually, as I mentioned, that the chemical lasers are very powerful lasers, like here. Weapon grade lasers. Now they have other solid state laser, but in the beginning when they started, because this was the dream for the Defense Department to have a weapon grade laser, so they use the chemical lasers. Okay, this is the action of the cavity. You can see here. This is your level, higher level. Okay, number of photon will be created, and this is your pump. Green pump is coming. Okay, and this is the gain medium. So you have two photons out. Now it started this process. Now you have so many. So this action is multiplying. These are excited atoms, okay? So they de-excite and get smaller. So this is the equilibrium. So you have a laser action, okay? Similar kind of thing here. If we just start. Like this here, you can see like this. Like this here. So this is a flash lamp here. Okay, when it shined on it, you can see these red, these photons. Okay, and like this here. It multiply, photon multiplying. Okay, so excited to the ground state. Again, it's flash, and then again multiply. This process is repeated. Okay, so this is how the laser action, and this is a flash lamp, how it's bursting. This is a pulse type of laser. Okay. Okay, so I think we can finish here, and rest of the part we will study in the next lecture. Okay, so I don't know how many people were there. If you have any question, Shoaib Mustafa, you were not here in the beginning.
Yes, sir. I was late, like 2 minutes. Sorry about that.
Okay. Not 2 minutes, more than 2 minutes, I think. Okay, so yeah.
Maybe.
Yeah. Okay, Gazanfar, are you here? I don't think so. See. Okay, if you have any question, please go ahead.
Yes, I have a question.
Hmm.
So in the laser, if you need to, for example, a red light output, you need to put the red coating in the two mirrors in order to the other types of lights can be cancelled.
Yeah, but you cannot say red coating. It's a certain coating, I mean, who reflect only red light.
Okay.
Okay. Yeah. Okay, so anyone
And
else? Yes.
the other question is when you have the AC or DC electrical discharge, this going to be useful for have continuum wave laser or pulse laser, or I mean if
Which
you
one?
use
Yeah, which one?
AC or DC?
Yeah, I mean, it depends on the what kind of laser you want to build. Okay, so some of the laser they need DC source. Okay, and some of the laser they may need AC source. Okay, and also it depends if you want pulse laser or CW lasers.
In this case, AC will be for
Yeah, it depends. Yeah, pulse. Yeah, or it depends on the frequency. Yeah. Okay, so anyone else?
Assalamu alaikum, sir.
Who are you? Hasnan?
Sir, Muhammad Adnan Sami, sir.
Muhammad Adnan Sami. It's a long, long time to listen to your voice.
Thank you, sir. Sir, how are you, sir?
Yeah, it's okay. Yes.
Sir, I just wanna ask about that we always said that the visible range is within 400 to 700 nanometer approximately. So
Yeah.
we also include that within 400 to 700 nanometer there are, I think, 7 different colors.
Yes. So
So is it true to say that basically there are not 7 colors, but these are uh, 300 colors? Can we imagine this thing, and can we deal this thing
I mean,
in laser?
if you know, actually, we consider 7 colors by sure. But if the colors are mixing up one color to other color, that could be, I mean, like you may have a different colors, but you cannot say that we have thousands of colors or hundreds of colors or something. Main colors are 7. So the laser also, you can have like around these colors.
So basically, sir, I was just thinking that whenever we go to a shop to buy any color uh, for painting or some other purposes, so what we can see that they give just number to the specific colors, code basically. So I think so. These are basically different colors, but the difference between them is so minor that we cannot observe with ordinary light,
With a
with
naked eye?
our with
Yeah.
our naked eyes.
Yes, you can say that differences, I mean, you cannot differentiate very minor kind of difference, bro. There may be many tints of orange or something like this, which we can, in this way is okay, but you cannot build the laser on this basis.
There may be some ways that we can work on it.
Okay, if you have any idea, we can discuss. because at the moment I don't have any idea that it can be done this way. It depends on the laser medium actually. If we can have different laser mediums, probably, but it's not a simple thing.
Sir, if we coat with a specific coating
The mirrors.
who allows just one color within the cavity to rotate, to oscillate.
This is what the dielectric mirrors. I mean, dielectric mirrors, even dielectric mirrors, you cannot make like this to differentiate between very, very small difference of colors. They are for the major colors, like a red for the green, yellow, or something. But in between, there are many colors which cannot be in. In future, Sami, maybe if we have very advanced technology, so we can have some mirrors and some dielectric coating, which can be, in this case, we can separate very, very small difference color spectrums, probably.
Sir, can you hear about or listen about ultra cold atoms?
I heard about it, but I don't know in detail.
Sir, basically, I just read about this topic. It is very interesting topic. We use ultra cold atom in quantum chips, in quantum computers, and many different quantum related fields. So I think there must be some laser systems in which we add these quantum terms which can make them able at this level.
Could be. I cannot say. I don't have anything to say about it because I don't know about it. So probably you can study and you can, if you can get some idea, probably you can express here and we can think. Because I don't have any idea about in detail actually.
Basically, sir, what ultra cold atoms are, we use them in Bose-Einstein condensate, and we basically trap these atoms by using lasers. We cool their temperature up to nanokelvins, and then we separate them one by one, and then we use these atoms in different applications. So basically we reduce their temperature, and by reducing their temperature their speed becomes very small.
Okay, Sami, but okay, probably we can discuss privately somewhere or something like this, because this is not a scope of this course. Or when we go to the application, we may discuss about this kind of, this is purely related to the applications of the lasers. So here I want the questions and discussion related to what I taught today. So probably we can, Sami, we can discuss other day privately or something like this, okay?
Thank you, sir.
Yeah, okay, if you have any of you question related to this, what we studied or something like this.
Hello, sir. Tisham here.
Okay, yes.
Sir, in the optical pumping configuration, the LF configuration was a very good idea because it has two focal points and all the laser light will be reflected to the second focal point. So we can get the maximum pumping from this idea. But why we use the axial pumping? I mean, in that case, most of the light will be lost. And
No.
I think
no, actually, no. Axial pumping actually. The first Ruby laser, if you remember in the last lecture, I show the configuration, I mean the Ruby lasers. So the Ruby laser was used and it was an axial configuration. Okay. So axial configuration is the rod is inside the flash lamp. Okay. And outside of the flash lamp is a tight kind of cavity. Okay. So ultimately light is reflected back to the crystal or the rod. Okay.
So
yeah.
Sorry, sir. What cavity is around the?
Which cavity you are saying? You are saying about the axial cavity.
Yes, sir. Yes, sir.
Still, it's not a cavity. It's arrangement of the like flash lamp, the pump source, and the rod, the gain medium. Okay, it's inside. Like this one is. If you go here, this one is this flash lamp is here. This one. So here, this one.
Oh, okay. Okay.
So rod is inside of this one. Okay, inside. Supposed to be.
Okay.
So
Okay,
it's very effective actually. Okay, so anyone else? Any questions? Because Ali is not here today, I think, who is used to ask the question. Okay, so Amna said, do you have any question?
No, sir. Everything was clear.
Arusa Hadi?
No, sir.
Okay. Okay, so
No, sir.
Mustafa, you have any question?
Sir, I don't have any questions, but I would like to share that this, the construction that you have shared here of the circular optical pumping method. There is a publication in Scientific American. I will share this in the group, which is interesting.
Okay,
It shows the construction of such a laser and how this actually works, which might be interesting for other people as well.
Okay, sure. Okay, so if there is no question, then Adnan Sami, I want to ask you one thing. Have you used any laser in your experiment, and which one was? Adnan Sami. Anyway, he left. Okay, so let's conclude here, and we'll meet on the next lecture. So probably, I want to speed up a bit, move to the ultrafast, but these basics are necessary because most of the people here, they don't know exactly the basics. So anyway, thank you very much for attending this class, and hope to see you in the next class. Okay.
Thank you, sir. Thank you,
Bye-bye.
sir. Goodbye.
Bye.